Hi guys, happy Monday. Um, Sorry I can't come in. It's a self-isolation, public health thing with my own kids. So that's the reason I had to set up. I know we were working off Schoology, but I said I would set up this one note. Just it's easier when you're making videos like this, and it's also handy then if you guys are out, I can put stuff in here, and it just allows you to see what I'm writing on the screen essentially, or drawing on the screen, just in case I need to highlight something. And if you remember, we've been working on atomic structure, the periodic table, and the flame tests, and this trends in the periodic table kind of finishes us with a guaranteed leaving cert higher level chemistry question. And what we'll do is we will be working on those then later on in the week. So at the end of this lesson, then this will enable you to finish that question set that I gave you last week. So you could do the atomic structure, you could do the periodic table, but I think it was in Unit 7, the last page in it you couldn't do, and this PowerPoint, which is also on the Schoology group for you to access, will enable you to answer those last questions. All right, so I'll just fight through this nice and quick, but you can have a read over it yourself, and this video is there for you, so you can go back over it if you so wish. Okay, so look, we're looking at trends. Basically, as you look at the periodic table, you notice certain things. So we noticed that there was metals and there was non-metals and there was groups, which showed us the amount of electrons in the outer shell, and then we noticed about the periods, and the periods are the number of shells. And then one more thing you asked me to look at again, and I will do that, but I want to do it in person, is the 1s2, 2s2, which is confusing, I know it is. So we need to have a look over that again, how to figure out that, and we'll write a few of them freehand, and I'm sure you'll get it after that for those of you who are finding it difficult. Okay, so this bit anyway, you have a couple of trends to look at. And number one there is the atomic radii. You know in maths, radii is plural for radius. So basically if you look, there's two chlorines stuck together. And what you have there's a radius there, there's a radius then going in from the other side of it, there's a radius there, and there's a radius there. So what you're looking at is from the center of one chlorine to the center of two chlorines would be two radiuses, or two radii. So you have a radii here and a radii here, so you have two radii. And the atomic radius of an atom is half the distance between the nuclei of two atoms with the same element joined together by a single covalent bond. So chlorine is joined to chlorine by a covalent bond, and you have a radius from there and a radius from here, and half of that then is the atomic radius. So basically from the center of the nucleus to the edge of the furthest ring would be, or orbital, would be your atomic radius. So here is the atomic radius on a periodic table. You'll notice in your log tables you have a few of these things, periodic tables. And you say, well, why do you need more than one? Because they kind of tell you different trends. So if you look at any patterns, up here they have the atomic radius. So the atomic radius is really small, it's white, and if it's really dark blue, it has a really big atomic radius. So if you look down at this column here, they seem to be quite a big atomic radius. The dark blue, so the atomic radius is really big over on the left-hand side. Whereas when you get over here, the atomic radius is quite small. Now, you'll notice through it, you have a few deviations in the color. So the atomic radius doesn't seem to get smaller as you go from left to right. In general, it does. It gets smaller. But there's a couple of things in there that get in the way of that trend. So a couple of things. One, the atomic radius gets smaller from left to right most of the time. And we're kind of looking at why. Why does it get smaller from left to right? And number two, why does it not get smaller from left to right all the time? Why are these anomalies in the middle? Like we had with the 1s2, 2s2 with chromium, there was different sublevels jumping when you fill certain orbitals. So, this is what I said. In general, they decrease across the period and they increase down the group. So atomic radius decreases across the period and increases down the group. So if you look at electrostatic attraction between the positively charged protons and negatively charged electrons, if the attraction is large, the protons pull the outer electrons nearer to the nucleus. So kind of read that again. If the attraction is big between the pluses, the protons, and the negative electrons, the protons pull the outer electrons nearer to the nucleus, giving a smaller atomic radius. So you think of like positives, opposites attract. So the protons will drag on the electrons, bringing them closer. That's why you get, and if you imagine if the electrons are pulled closer to the protons, which are in the nucleus, then the atomic radius is going to get smaller. So that's really the reason that atomic radius decreases across the period and then increases down the group. So the additional electrons are going into a new energy level. So remember this 1s2, 2s2, 2p6, 3s2, all that? So going to a new energy level, and the outer electrons are becoming further away from the nucleus. So if they're going as they go up in energy level, they get further away from the nucleus. So you imagine in sodium, the two electrons, the first two that go on are really close to the nucleus. Whereas if you have the poor outer electron, the one that it's always trying to get rid of, that's really far away from the so it's going to have less of an effect from the protons. So number one is the additional electrons, and number two is you have the screening effect of inner electrons. So if you think of an atom, whereas say we stick with chlorine, and you have the electrons that are right in here. So chlorine is 17 electrons, so it's 287. So you're going to have 2, 3, 4, 5, 6, 7, 8, and you have the 7 electrons out there. So if chlorine has 17 protons, so that means it has 17 positives in here in the middle, and that hangs on to those 17 negatives all going around the outside. What this screening effect means, it's that all these positives in here are going to have a much greater effect on the inner electrons than they are on these electrons out here, because they're further away. So the way I worded it there in the notes, there are more protons and electrons as you move down a group. The inner shells help to shield the outer electrons, allowing the atomic radii to be bigger. So if we have our electrons out here, if the protons don't have a really strong effect, they can move further away from the nucleus. So they can move further away, and that means the radius of chlorine gets bigger. Okay, and there's a couple of examples of different atoms. A couple of reasons atomic radius decrease from left to right across the period. Number one is because you have increasing nuclear charge. So the number of protons increase from left to right. You know that. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. So it goes 1, 2, 3, 4, 5, 6, 7, 8. Because of that, there is a greater attractive force on the outer electrons, drawing the energy level closer to the nucleus and decreasing the atomic radius. So because you have increased nuclear charge, you have decreasing atomic radius. And as you go across, as you go across one period, so say you start at sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, they may be adding electrons, but they're being added to the same level or the same shell. So because they're being added to the same shell, you don't have any extra shells being added on, therefore you have no screening effect. So that's two reasons why you have the both. So some examples there for you to have a look at. Okay, and you can have a look back over that and we can talk about that again. The other one is electronegativity, and it's kind of the same thing, to be honest with you. The power of an atom to attract electrons to itself. So the amount of power that an atom has to attract electrons. So electronegativity, if you think of electronegativity, positives in the nucleus, negatives on the electrons. So how much power have those protons, those positives got in order to attract more negatives? The higher the value, the more electronegative the element. So fluorine is the most electronegative. And again, in your log tables, you have an electronegativity table for all the elements. So fluorine is extremely electronegative. It has a value of 4. Here's our scale, and this is in your log table. So if they ask us about electronegativity values, we're not going to have to remember these as well as the atomic numbers. Here's our fluorine there. I'm not sure if you can see me highlighting. You can. Fluorine has 4. Over on the left, if you have a look, lithium's 1, beryllium's 1.5. You see the trend? Boron's 2, carbon's 2.5. So electronegativity is increasing across the group. The way people tend to remember these is electronegativity increases across the group, and that's the opposite to the atomic radius. And they're kind of related. Because the electronegativity increases, we get smaller atomic radius, or because we have smaller atomic radius, we get increasing electronegativity. So there's our electronegativity sentence. Decreases across the group and increases across the period. So if I go back to my table, I already wrote increasing across, and as we go down, we get a decrease. Okay. Why? Kind of the same reasons as the atomic radius. So the electronegativity decreased down a group because the atomic radius is increasing. So the outside electrons are becoming further away from the nucleus. There's a smaller force of attraction between the nucleus and the electrons. Bigger atomic radius means lower electronegativity because of the shielding effect of electrons. So the screening effect shields the outermost electrons. So if you can remember this for atomic radius, it'll work the same for electronegativity. And therefore, there's increased screening effect, which means we have decreasing electronegativity. Kind of the same idea. They increase across a period because as you move across a period, the attraction between the nucleus and the electrons becomes greater. Why? Well, what happens as you go across a period? Because you're getting more protons, means you're getting more electrons, which means you're getting more electronegativity, more force, more strength of those protons able to hang on to the electrons. And decreasing atomic radius means the electrons in the outermost shell are closer to the nucleus, and then there's more attraction between the nucleus and the electrons. But just remember the trends. Electronegativity increases across the group and decreases down the table. Atomic radius decreases across the period and increases down the table, for the same reasons for both. The third one, ionization energy. Some elements, things like sodium, potassium, we spoke about these a lot, your alkali metals. Remember these ones? We'll chuck these into water at some point and see how much they want to get rid of that outer electron. They want to get rid of that, and they're mad to get rid of it. And it's very easy for them to get rid of it. And for that reason, they're extremely reactive. And we spoke about these in detail. Other elements such as gold and silver, no interest. They have no interest. They're like carbon. They afford to get rid of. They afford to get. So therefore, they're extremely unreactive. So your ionization energy, if you think of gold and silver being so unreactive, and sodium and potassium being so reactive, why? The first ionization energy of elements, you got to learn this, is the smallest amount of energy required to remove the most loosely bound electron from an isolated atom in an element in that gas state. Basically, what they're trying to say there in normal human language is that it's how much energy you need to put into something in order to get rid of one electron off it. So we relate that to if we relate that to sodium, back up here, it's not going to take much effort, drop of water for sodium and potassium, and the ionization energy is so low that the electron will pop off into the water. Whereas gold, silver, their ionization energy is going to be massive. They're not bothered getting rid of electrons at all. So that's what ionization energy is. The amount of energy required to move the most loosely bound electron. Okay? And you can imagine if the first ionization energy is that, the second ionization energy would be the energy required to move a second electron. Third ionization energy, third electron. So if we have sodium here, sodium there becomes Na+. Remember, anything that loses an electron becomes a plus. And there's our little electron that flew off. And we move again, we bring this Na+ down here. Here's our Na+. We take another electron, it becomes Na2+. You might remember doing magnesium oxide in junior cert, same deal. And our electron coming off again. So there's two electrons dumped off, one in the first equation and one in the second equation. So here's our rule. Ionization energies ionization energies increase across a period and decrease down a group. Increase across a period and they decrease down a group. And kind of these slides are kind of overkill. Once you know the general rules about atomic radius, electronegativity, and ionization energy, that kind of covers it. But anyway, here it is: the reasons ionization energy increase across a group. So, we're going back to atomic radius and see these are all linked. As the atomic radius gets larger down a group, we know that atomic radius increases down a group. So the electrons are further away from the nucleus, then it's easier to remove the outermost electron. So we only need a small amount of ionization energy. And this, our old friend, the screening effect, as that increases down a period, so the outermost electrons are not influenced by the nucleus, and then less energy is required to remove them. The opposite of that then, why ionization energy increases across the periods, well, you have more charge. So the number of protons in the nucleus increases the attraction between the nucleus and the outermost electron. And we know that sodium has one electron, dying to get rid of it. If we go into group 2, something like calcium has 2 electrons, wants to get rid of it, but not as bad as sodium and potassium in group 1. Once we get into the middle, carbon, they're not gone. They know they're in too deep to lose 4 or gain 4. So increasing nuclear charge means it's easy to remove 1, but once you get to group 4, it's almost impossible. And we also know that the atomic radius is decreasing across a period. So the atom decreases, the outermost electron gets nearer to the nucleus, more influenced by the attractive forces, and then more energy is required to remove the outermost electrons. So all these are linked. Here's the ionization energies. So if we take, so if you have a look at that graph, there you have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. There's our first 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, up as far as calcium. So you can have a look there. Our ionization energy, hydrogen to helium, is going up. So helium, is on the top right of the periodic table, hydrogen's top left. Then we start at period number 2, lithium, beryllium, boron, carbon, nitrogen, oxygen. So the general trend is that it's going up from left to right. Then it starts at sodium, magnesium, and general trend up as far as argon, left to right. Okay, so there's our general trend. Kind of an explainer of the whole lot. Maximum value, the biggest ionization energies, of course, are for the noble gases, have no interest. You want to take an electron off helium, it's going to kick up an awful fuss. Very, very difficult to do. Massive amount of energy required. The minimum values are for the alkali metals. As you know, 1 electron, small ionization energy, large atomic radius, small electronegativity. So in general, ionization energies increase across a period and decrease down a group for the same reasons as we've said 2 or 3 times already today. Okay. The exceptions. There's always exceptions, as you know. 2 exceptions. Things like beryllium and magnesium. So these 2 here have abnormally high values. That's when you look back at the graph. You can see there's a few kind of jumps and troughs in the graph, because the most loosely bound electron comes from a full s orbital, and we'll draw these out now on the board maybe the next day. So if the s orbital is full, we get this things going from 4s to 3d and 3d to 4s, because you want to fill them one at a time. That's what I want to do again. So here's 1s2, 2s2, 2p6, 3s2. Group 5 elements as well have high values, and that's because the electrons being removed are from exactly half filled. Remember, there was 2 reasons that happens. If it's full or half full. So remember, you have 1s2, 2s2, 2p6, 3s2, 3p3. So this whole thing of being half full, this 3 causes it to have a high ionization energy because it doesn't want to lose an electron if it's exactly half full. Okay, and there's a summary there for you to have a look at the trends in ionization energies. there's kind of what we've been saying. The ionization energy increases across the group and it decreases down the group. And you can have a look at these numbers. Generally, you're going from 3, 4, 5, 6, 7, 8, 9, 10. So you can see the ionization energy increasing from left to right. And so you can spot those deviations that are from the half-filled S&D sublevels. Okay, another table there for you for the higher ionization energies. So going from sodium, so you can see sodium 496, 738, 578, 787. So this is aluminium, which is going to be group 3. So if we drew out the 1s2, 2s2 for aluminium, we'll see a reason, something to do with a half-filled SP or D sublevel that is going to cause that that high sublevel, that high ionization number. Okay, so what I'm going to do now, I'm going to let that will be enough for you to go and do your questions. The rest of what we have underneath there is just examples and solutions of different questions that that have come up in trends in the periodic table. And they're there for you to take a look at. What I want you to spend the rest of the class doing and to have done for the next day is to finish those questions on trends in the periodic table. And what I'm going to do is I'm going to put together the exam questions on the atom, anatomic structure, and the periodic table. The last thing I want to do is to go back over those 1s2, 2s2, and that should be the equivalent to 3 chapters for us done, which is not bad by the 20th of September. We'll try the exam questions on that and then go on and look at some titrations and acids and bases. Okay, thanks, mind yourselves.